Hello, I'm Thai. I'm from Hanoi University of Science and Technologies. Today I will present about my product in DSP Contest, implementation of fractal image compression on DSP. First, I will talk some information about these methods. Fractal image compression is a lossy compression method. It compresses image by reducing redundancies in space domain of an image. This method is based on the contractive mapping fixed point theorem in mathematics. Fractal image compressions provide many interesting characteristics, including one of the biggest disadvantages is low coding speed. It means that it takes a long time to encode an image. But this method also provides many wonderful advantages like fast decoding speed and resolution independent, etc. Here, resolution independent is mean you can decompress an image with any resolution you want. Now I will talk some basics of fractal image compression. In this method, an image is divided into many domains, DIs. These domains can be overlapping. Such image is also decomposed into many ranges, RIs. These ranges are not overlapping. And for each range RI, we will find the best match domain DI. The worst best match here is meant is most similar to. Then we calculate a corresponding transformation Wi of the pair of RI and DIs. Here I show a example of DI and RI block. Here this equation shows all the coefficients of the transformation Wi, A, B, C, D, E, F, and O. These coefficients will be saved in the compressed file. And a set of all Wi called W is the transformation of the image. The image F that satisfies the equation F is equal to W of F is the fixed point of W. In addition, if W is contractive, F is unique and an approximation of the original image. Thanks to these properties, when decoding we only need to find a fixed point of the transformation W. By integrating the equation, Fn is equal to W of Fn minus 1 with any initial image above. Here I show the way to create a set of range R. There's many ways to create, but I choose a quadtree algorithm is one of the most effective way to use in this implementation. Here I show some example of domain DI. You can see here there can be overlapping. Because of the low speed, so there's many speed up methods has proposed. Easy implementation, I use two speed up methods of Fishers and Hudsons. The key thing is both speed up method is we divide the set of range and the set of domains into many subclasses, and for each range we only search for the best domain in the same subclass. Here the Fisher speedup method use 72 subclass, and the Hudson's ones use 360 class. Now I show some feature of the DSP TMF3 throughout C515. The program will be loaded into this DSP chip, and the compressed and decompressed image will be saved in the micro SD card here. Here is a block diagram of the encoding process. An original image .raw will be transferred from computer to the DSP and be processed here. The result is the compressed file .efs will be saved on the memory SD card. I run the encoding process with many different parameters to get different compression ratios and measures the encoding time of each time. Here is a graph to show that. We can see that the Hussen's methods need a longer time than for the Fisher methods here. But in the area that the compression ratio is high, you can see the encoding time of both methods is quite the same, because when the compression ratio is high, the number of comparisons to find the best domain is small, so the encoding time does not much depend on this number of comparisons. It depends on the rate of the DSP. Here's a block diagram of decoding process. The compressed file .efs from SD card will be loaded to the DSP chip and be processed here. And the result is the decompressed image .raw will be saved again in the SD cards, and this image will be shown on the computers using MATLAB. I also calculate the PSNR to show the quality of the output image in the decoding process. We can see for both speed-up methods, the PSNR is quite the same for both image Lena and San Francisco's. Here I show some graphic result. Is the output image of each method. Here is a Lena image, the output image of the Hudson's method, Fisher method, Hudson method, Fisher method, and the last one is the original method. The same way for San Francisco image. Here each output image have a different parameter and different methods, speed up methods. Here I show the interesting process for decoding. This output image in the first time, the second time, the fifth, the 10th time, and the 20th time. The same for the San Francisco image. You can see the PNR will be increased step by step, and the image will have more details after each loop. I give some remark here. Hudson method and Fisher methods provide nearly the similar PNR or the similar quality of output image, but the encoding times of Hudson method is quite longer than the other. So we can conclude that on this DSP, the Fisher method is more effective than the Hudson method. Finally, I would like to thank you, Texas Instruments and DSP Summer Schools, by donating this kit for me to implement this image compression. And thank you for listening. Now I will demo my product. This is a DSP kit and it is connected with my computer through the USB cable. I use code composers to compile my code, and the program file .out will be loaded from my computer into this box. Now I will run it. Here I have to choose some parameter for the encoding algorithm. This parameter will affect the quality process and affect the quality of decompressed image, and the encoding time. The first parameter is entropy threshold. I choose 6, and the root mean square threshold I will choose 6 as well. And the mean size I choose 4, and the max size I choose 16. This size is the minimum size and the maximum size of the range block. And the next two parameters I choose 0 and 0. It means that I only search to find the best domain in one subclass. This time I run the code with Hudson speedup methods. You can see each step of the process here. After compress the image successfully, I write the data on the SD card, and I show the number of transformations, the number of comparison, and the number of bytes written in the compressed file. I also saw the compression ratios. Now is equal to 6.42 to 1. I also saw the encoding time is 18 seconds. I have implemented the Hudson's speedup methods, and now I will run the Fisher's speedup methods. After load the program with the Fisher speedup methods into this board, I will run it. In the same way, I have to choose some parameter to the encoding algorithm. I will choose the same parameter as the parameter I choose for Hudson's methods. The entropy is also I choose 6. Root mean square I choose 6. The mean size is 4. The max size I choose 16. And 0 and 0 to search only on one class. And here is the result. I saw the number of transformations, the number of comparison, the number of bytes written in the compressed file, and the ratios is 6.4 to 1. It's a little bit less than the compression ratio of Hudson's methods, but the encoding time you see here is 15 seconds, is much less than the encoding time of the Hudson's methods. After running both speedup method to encode the image, I implement the decoding algorithm on this board. I use Code Composer Studio to compile the decoding code, and then the program file will be loaded from my computer into this board. Now I will run it. Here I have to choose the number of iteration using in the decoding process. If this number of iteration is high, the output image will be approximate the original image. Here I choose 10. You can see each step of decoding process. Here I have to choose a name for the decompressed file. Here is the result. The name of the decompressed image, the PNNRs, and the root mean square below. All these numbers is in decibels. I also saw the decoding times is 10 seconds. It's quite fast with the encoding times.